All right, let's start. Good morning, everyone. I'm Dorsa Sadig. I'm an assistant professor at Stanford, and I'm chairing this session. So this is session 11. This is a session after banquet for people who made it back. And our first paper is Impact-Friendly Robust Control Design with Task-Based Quadratic Optimization. This is work by Yu Quan Wang and Abderrahman Khettar, and Abderrahman is giving the talk.
So thank you very much. It is a joint work with Dr. Yuquan Wang that couldn't make it for. Can I have a picture here or for the conference? Do we supposed to have something here? Because otherwise I cannot see what's behind here. Yeah, no problem. No, it's still like it's blue. But it changed the color. Oh yeah, it's showing this. Now it's showing everything. Perfect. Good. So in a few seconds, you will see a video of our humanoid robot, HRP2, performing a task for the preparation of the DARPA challenge. And you won't be surprised to see a robot having that slow motion. And there is 3 reasons for that. The first is that generally you have a perception that doesn't work at the closed loop control, and if you want to do feedback, so you are obliged to deal with this frequency. And then the second one is that whenever you get the pose, the robot can go faster, but you know that the robot will contact, and then you will decelerate, so you will go slowly because you have a contact. And the reason why there is a contact, so it reduces impacts, and generally robots now fear impacts, and the researchers too. Why? What's wrong with impact? First, it's instantaneous, even for very small velocities, and the second is that it's too fast to do anything with the control part. So then it's supposed to be compensated. So in this video, you will see, in fact, our QP controller in which we put a very simple task to a reaching set point task, and then we put a wall randomly, and the QP is not aware that there is a wall, and what happens basically is that the QP is just unstable. So if you want to deal or do high impacts with your robot, so you have to modify the hardware to keep your controllers, or you have to work in the controller if you cannot really change the hardware. But in fact, what happens really is that we looked carefully about what happenings in the QP when the impact or unexpected impact happen. And in fact, there is a jump in the velocity of the states, okay? And then this high jump would do that some constraints will not become feasible. And then the solution couldn't be found for the QP, so that he cannot generate, in fact, the solution. And sometimes it just became unstable because of the jump of the constraints that makes it just go crazy. So you have two ways, in fact, to deal with this. So we have thought about how we can do that. And so we come up with a simple idea that, OK, since we want to keep our QP because it has really nice features to do or deal with many other things, like visual surveying, force control, etc., we will try to predict the impact and then integrate the model of the impact inside the QP. Then we do a prediction of the impact. We predict what would be the velocity after the impact, and we assume, in fact, that we will have an impact at the next iteration. Since we don't have reliable 3D models for impact, we are using a point impact, and we have point contacts anyway. So then we took point impacts, and then we compute the velocity, actually, after impact, and we integrate the difference between the velocity after impact and then the velocity after and the current velocity as decision variable in the QP. And then we say, OK, compute the acceleration of the motion, assuming that you will have these margins, okay, of jump in the velocity. Then the things behave nicely well. Now, if you take this example, you will see that the robot is performing the things, and when you use our controller on the left, even pushing the object on the right down part, so you see that the QP stay stable. But of course, it reduces a bit the velocity because now he knows that if he go faster, it might not be, the QP might not feasible, and he might even violate the integration, so the limitation of the hardware. So by the time of writing the paper, of course, we did demonstration and simulations only on the simple robot. Then we went faster now. We embedded other constraints, and we did experiment on the HRP4 robot that we have at Lyon. And as you can see from the video, everything is going well. Our contribution is that now we enhanced our QP controller with impact awareness, and then without the use of any reset map, any accurate impact timing allocation, and no offline trajectory generation as usually done in control. So now you can go to impact without feeling anything in your controller and even on your robot with maximum velocity that is allowed. So I have a bunch of future work and also of drawbacks. Please come to my poster and we will discuss them.
All right, so the second talk of the session is a dynamical system approach to motion and force generation in contact tasks. So this is work by Walid Amanhoud, Mahdi Khorramshahi, and Aude Billard, and Walid is giving the talk.
So hello, I would like to present you, my name is Walid, so I would like to present you this work, which is about using dynamical system to generate motion and force in contact task. So it is a joint work with my colleague Mahdi Khorramshahi, and it is supervised by Professor Aude Billard. So in this work, we work with time invariant dynamical system, which takes as input a position and gives as output a desired velocity. Here on the right, you have an example of a dynamical system which allows to reach a fixed target on a plane. When using the DS in a closed-loop configuration, a robot can follow the flow of the DS while being robust to real-time disturbances, as it can immediately replan its trajectory from any location in space. However, one limitation of this time-invariant DS framework is that we can only control motions. So now, let us consider that we have a non-flat surface and that we know the normal vector and distance to the surface. We assume that we have a nominal DS, f of x, that allows a robot to go to the surface, move on it in order to go to a target, for instance. What we would like to do is to generate a contact force when the robot is moving on the surface. To this end, based on the desired force profile that we want to apply on the surface, we compute a normal modulation term, fn of x, that will locally change the flow of the nominal DS close to the surface. As a result, a robot can come in contact with the surface, move on it while generating contact forces. With this approach, we can perform contact tasks while being robust to real-time disturbances in all phases of the task, in free motion and in contact. And we make sure that passivity is preserved for the use of energy tanks. So we did a first experimental evaluation on a task where a robot should come in contact with a non-flat surface to perform a circular motion around a fixed point while generating a desired force profile. So on the right, you have the desired unmeasured force profile. At any moment, a human can come and take the robot away from the surface without generating instabilities. The robot just comes back to the surface to perform the task again, following the flow of the DS. The human can apply disturbances to the robot while it is moving in contact. The robot is robust to the disturbances and stable. Also, we can apply disturbances to the environment, to the surface in that case, and the robot will smoothly comply to the disturbances and still achieve the task. After that, we did a more challenging task where this time 2 robots should reach and grasp an object by generating contact forces, and then there is a human that comes and interacts with the system. On the right, you have the desired unmeasured forces of the 2 robots. So the interaction is safe. The human can change the pose of the robot while the grasp is maintained. Both robots are stable and compliant. At any moment, the human can break the grasp without generating instabilities. The 2 robots will just reach and grasp the object again if it is reachable. And here, this is a similar video where this time the two robots reach, grasp, and lift the object to a predefined location. Then there is the human that can change this location through a graphical interface. So as before, the robots can move with the object while maintaining the grasp, but at the same time, we have a system that is compliant and stable, as the human can come and apply large disturbances to the robot that comply to them and that try to maintain the object grasp as the desired location. Thank you for your attention, and if you want more information, come to us later to the poster session.
Okay. All right, so the third talk is going to be on direct drive hands, force motion transparency, and gripper design. And this is work by Ankit Bhatia, Aaron Johnson, and Matt Mason, and Ankit is going to give the talk.
Good morning, everyone. Today, I will be talking about direct drive hands and how we can improve force and motion transparency in grippers. To begin, let's talk about what hands are for. If your answer is grasping, you will normally pick a vice-like gripper, something that can handle large external disturbances. But hands are for more than just grasping. They're for interacting with the environment. For grasping, we normally consider clamping force and payload, and that's as a priority. This results in large gearboxes, and therefore we get a torque multiplier, but we also get high reflected inertia, large backlash and friction, and lower speeds. We also lose transparency, which is how well we can transmit force and motion between the hand and the task. To add that transparency back, we resort to using active or passive compliance. So we take a transparent source, which is the motor. We reduce the transparency by adding a gearbox, and then add the transparency back by adding a series spring. Another approach is to use direct drive, which is basically connecting the motor directly to the task. This approach is becoming increasingly popular with improvements in motor technology. There are a few benefits of using direct drive actuation. Mechanical simplicity, higher speed, and zero backlash are obvious consequences of the gearbox delete. To explain improved transparency and force control and sensing bandwidth, we use empirical arguments and a first principles model. More information can be found in the paper. We design a 4-degree of freedom direct drive hand with off-the-shelf brushless gimbal motors. The hand is capable of using censored field-oriented torque control and high-speed operation. One advantage of using direct drive is that you get variable compliance effortlessly. Moreover, due to low reflected inertias, you have a light touch. To test and validate the benefits of direct drive actuation, we encode a smack and snatch grasping behavior. The hand smacks into the table and snatches the object so quickly that the arm never has to stop. The fingers act as a contact sensor and manage the collision impulse. The grasping behavior takes about 10 milliseconds and is robust with a success rate of 86% over 50 trials. One benefit of using this method is that it is completely robust to changes in table height without any additional parameter changes or encoding any other behavior. It is also sort of robust to size and shape discrepancies, which you will see in the next video. While the DD hand gains in speed, transparency, and bandwidth, it might lose out in gripping force. To mitigate this, we envision overdriving the motors with active or passive thermal management, and utilizing kinematic singularities and directional rigidity to offload them. I look forward to talking more about this work at my poster today. Thank you.
Okay. Our next talk is modeling and analysis of non-unique behaviors in multiple frictional contacts. So this is work by Matthew Holm and Michael Poza, and Matthew will present the work.
Hello, everyone. I'm Matt from the Grasp Lab at UPenn, and this is joint work with my advisor, Michael Poza. The fundamental physics of locomotion and manipulation is the generation of contact forces with the environment, a large portion of which can be generated near instantaneously in impact events. So if we like to create reliable motion on our robots, it's important that the predictions of these behaviors match reality. Unfortunately, even our most simple models of impact behavior are riddled with inconsistencies, such as non-uniqueness under simultaneous impact. Consider, for example, one of the simplest models of dynamic walking, a rimless wheel. And if we throw this object into the ground on 2 feet simultaneously, we might ask what happens after an inelastic impact. One thought process might be that there's an equal force on the left and the right because the system is symmetric, bringing the object to rest. But just as easily, we could have employed a sequential argument, either doing an impact at the left than the right or vice versa, and obtained categorically different solutions of rolling off of 1 foot. There are similar inconsistencies in much more complex models in the literature, and model non-uniqueness often pairs with extreme sensitivity in real-world systems. Many of the fundamental problems in robotics are underpinned by multiple contacts and friction, so if we'd like to create reliable control solutions to them, it would be useful to have a model that can generate all of this non-uniqueness. So we contribute exactly that, a model of simultaneous rigid frictional impacts, and critically, we prove existence of solutions to our method, which has been shown in the context of simulation before, but those methods focus on producing a single reliable result, whereas we're capable of capturing all of them. The theoretical basis for a model is Ralph's original 1891 single impact model, which takes a pre-impact velocity and incrementally and simultaneously discovers a post-impact velocity and contact impulse by continuously increasing the impulse from 0 until a valid post-impact state is achieved. It does so by following a flow field on the velocity space derived from Coulomb friction. For example, we could consider a single block impacting the ground with rightward velocity. We plot the corresponding flow on the right in yellow. We see that for our initial state, it points upwards as normal forces resist penetration, and to the left as friction forces resist sliding. Following this process results in a terminal velocity of 0. We create for this work a natural, extremely permissive extension of this model to multiple impacts by allowing Ralph's method to evolve them at arbitrary relative rates. More precisely stated, we query Ralph's method for flow directions for each active impact, and then select any flow direction in the convex hull of these vectors. We can revisit our simple example of the rimless wheel, and we not only discover the 3 solutions we discussed before, but also every reasonable intermediate solution shown in this green non-convex set. We also see subtle non-uniqueness in simple manipulation scenarios, such as pushing this yellow block into the wall on the right, and we are able to produce both of the green post-impact velocities. This process can be described as a differential inclusion, which is like an ODE, except the derivative is only constrained to lie in some set. This model is provably well behaved. It dissipates kinetic energy. There's a homogeneous relationship between pre and post-impact velocity. And most critically, we prove existence of solutions for every pre-impact velocity. But because of the way that we interpret these solutions, we must also show that they eventually reach a valid terminal state for the impact. And our key theoretical result is that this is always true for a wide variety of scenarios in locomotion and manipulation, making our model widely applicable. In summary, we've developed and presented a rigorously derived model for simultaneous impact. For future work, we're going to generalize it to elastic impacts and embed it in the full dynamics of rigid bodies. And we have some ongoing work on computing this post-impact set, both from a reachability and simulation perspective. Thanks for your time, and I hope to see you at my poster.
Okay, and then the final talk of the session is VIMO, Simultaneous Visual Inertial Model-Based Odometry and Force Estimation. So this is work by Barzan Issar, Philip Fone, and Davide Falanga and Davide Scramozza. And Philip is giving the talk.
Hi, I'm Philip, and this is VIMO, our simultaneous visual inertial and model-based odometry and force estimation. This is joint work with my colleagues Barzan Issar, Davide Falanga, and Professor Scramozza. Drones nowadays often target applications such as manipulation, transportation, or inspection, where they need to detect interactions like picking up a package or grasping. Common approaches use visual odometry for localization and an additional estimator to recover the interaction forces. but they neither exploit the known system dynamics nor jointly estimate the external forces to reduce uncertainties. We want to change that and set our goal to improve visual odometry by jointly estimating the external forces based on the known dynamics. Now, state-of-the-art visual odometry often uses pose graphs, where states at multiple time steps are linked through IMU and visual key point measurements. They jointly estimate the robot state, the IMU bias, and the visual key point locations. But they don't account for the actuations, since it is often subject to large disturbances. However, for many tasks at hand, we need to know these disturbances. Our contribution now is a relative motion constraint based on the actuated and the external force that we put into the pose graph. Since we know the actuation, we can recover the external force on the platform and also improve localization accuracy. For this, we first formulate the accelerations. On the left-hand side, we have the measured accelerations, and on the right-hand side, the actuated accelerations. Now, many approaches have found that the actuation, especially on a drone, is too disturbed to be of real value for the estimation problem. But they do not consider the external force acting on the platform, which we now want to put back into the equation. To add this to our pose graph, which we can solve with optimization techniques, we formulate a dynamic residual. To process the high rate actuation information, we actually apply a little trick. We split the residual into two parts, where the first part only depends on optimization variables, like the robot state, and the second part only depends on measurements, like the IMU or the actuation data. Therefore, we can pre-compute this second part independent of the optimization terms and solve it very efficiently. Now, to verify our approach, we use a Quadratic system, and we do experiments in both simulation and real world with a motion capture system. We show that this approach can improve the localization accuracy up to 30%, and this comes at no additional computation time. Moreover, we could also apply this approach on other robots, like probably underwater, space robots, or even manipulators. Now, to verify our external force estimation, we additionally track a force sensor in a motion capture system. Then we poke our drone to recover ground truth external force data. We show that we can estimate the external force accurately in both direction and magnitude on the drone. Now, with this, I already want to conclude my talk. And we introduced a pre-integratable dynamic residual based on the actuation and robot dynamics that can not only estimate the external forces, but also improves the localization accuracy while not causing any additional computation time. We are going to open source this approach soon, and with this, we are looking forward to see some more interesting interacting robots, and I'm looking forward to interact with you at the poster session. Thank you.
All right, let's have all the speakers up here. And questions. There's one right there.
For the second speaker, could you comment on what the relation is between how accurately you know the location of the surface and how accurately you can apply a force?
So on the experiment that we were doing on the surface, let's say the root mean square error of the force, it was between 2 and 3 Newton. In fact, in our model, the normal modulation that we are using, it's like a feed-forward term. So there is no feedback of the force to make it more accurate. But actually, I mean, this depends on your task and on the tolerances that you have on your task. If the force error is higher than the tolerances, okay, you can start to introduce the feedback of the force, and it's gonna work like we did it, and you can really track the force correctly. I don't know.
Any more questions?
Question for Philip. So, amazing work. Did you guys worry at all about observability? In the sense that in some cases, I imagine that you have troubles distinguishing, identifying the forces, the biases.
Yes, good question, thanks. We actually discussed this in the paper. So there are other works that prove, for example, the observability theory in postgraphs or other visual inertial estimators. When it comes to external forces, there are some funny behaviors, like it gets tricky to estimate very long constant external forces because there is an ambiguity of long constant forces and the IMU biases. But you might find more information about this in the discussion section of our paper.
Questions? There was one back there.
One question for the fourth speaker. What kind of schemes do you use for the simulation of the differential inclusions, and what order of accuracy you have thereby? Thanks.
Right. So we don't have anything that's over first order accuracy at the moment. With differential inclusions, you can sort of simulate them with like Euler methods as differential equations, but we also have a time stepping method in the work that will prevent some of the sort of categorical issues with simulating non-smooth systems.
Any more questions from the audience? Okay, I have a question from Ankit. So what are some of the limitations of this direct drive actuation? Like, do you get any loss of torque? Any?
So the first thing you want to care about is how much torque you can apply. And that's a sort of a limitation, because as you go higher and higher with direct drive and you want to apply more and more torque, your motor becomes bigger. So there are these second order effects that we haven't yet looked at, and I think there is some work out there that talks about it, but there's no concrete work about how motor dimensions actually scale, and if you were to apply more and more torque, how do you like make the actuators actually dense, torque dense?
Yeah. And if there are no questions, I have a question from Abdurrahman. So you actually have it on the robot now. So what were some of the challenges? Because at the time it wasn't. So what are some of the challenges of putting it actually on the robot, and what are the things you did?
Well, the challenge, I mean, first of all, the constraints we have when to apply our method is that to get the data. I mean, if you cannot ask the robot provider, so let me know what is the maximum impact that the robot could absorb by the hardware, so that we integrate these constraints. And yeah, it's hard to get this information actually. So for our robot is even harder because it's not a commercial prototype. It's a prototype, it's not a commercial product. Then you have also the issue of, we discovered that if you have full unilateral contacts, then obviously you have to sustain the other contacts that serve as a support if you want to use one of the contacts to go. And then obviously for the stability, you have to make sure that you have a model not only of the impact, but also of the propagation of the impact inside the structure, so that you keep the contacts still. So we are discovering a lot of interesting things, really, and it's challenging to do the experiment with this, because you can block your robot, of course. But otherwise, no, we are having a lot of fun, and we are trying to do other experiments, like swiftly like grasping a box that is coming on a conveyor and putting it like abruptly, as we humans do naturally. I mean,
That's awesome. Cool. All right. So if there are no more questions, let's thank our speakers.